Okay, good evening and welcome back to this last lecture. Before we start, let me just remind you that you have 2 fields of assessment test on ILS website, probably for all courses of ILS, and also deadline for these reports. The ultimate deadline is August 10. After this, I don't take any report. Okay, last week, let me quickly remind you what we have seen. We first introduced some graphs with n vertices. This is a set of all simple graphs with n vertices. A graph is a set of vertex and a set of edges. And I introduced or recall the notion of path, maximal connected components, and so on. And then we have TU games with communication graph. So it's a TU game, but in addition with a graph where we know which player can speak with which player. So we know the relation between the players. So TU game with communication graph is a set of n players, this function v that we have for all TU game, plus a set of edges which give us these connections. And the set of all TU games with communication graph is denoted by CGN. And I also introduced the notion of connected coalition. Then we want to define allocation rules, so how to distribute the payoff. So I introduced the notion of component efficiency, the notion of fairness, and this notion of stability for these games with communication graph. And there is also a definition of one TU game which encodes this information about the edges. There was a small mistake in the notes. It was not clear, let's say. It was not clear, and thanks to a student, it has been clarified. So there is a precise definition for this game. And once you have this game, you can define the Meyerson value based on the Shapley value for this game. And it turns out that there is a unique allocation rule from this set of games with graph to Rn, which satisfy the efficiency, component efficiency, the fairness, and the stability in some cases. Okay. Then we move to examples. So the first example, to the last section, last chapter, I just mentioned that in some cases, instead of utility games, we have to deal with cost games. It's essentially minus a utility game, but things are quite similar. Then I introduced a first example, which is this airport problem. I explain what it is. During this section, I explain what is a convex game. The good point with convex games is that their core is not empty. And in addition, the Shapley value is inside the core. And this is not true for all games or all TU games, but at least it's true for convex games. And in particular, this airport problem, when you recast it in an airport game, it is convex. And the solution is given by one solution is given by this Shapley value. The good point is that this is a natural solution. We can understand it. It's meaningful, and you for free, because it's a Shapley value, you get the 4 properties that this Shapley value has. Then I introduce a second problem, which is this bankruptcy problem on the related bankruptcy game. It's now made of 3 ingredients. You have the set of n players, you have the estate, or what is left after bankruptcy, and the claims from the n players. So each player is claiming something, and you want to distribute the estate or the remaining money among these players. And it turned out that this estate is less than the sum of all claims. So you need to distribute in either fair way or in a certain way, but satisfying some conditions. And I introduced, so it's the way to distribute. It's an allocation rule, but in this case, we call it a division rule. So it's from this set of bankruptcy problem to Rn, and it has to satisfy two conditions. Each player receives at most what he claims, and at the minimum is 0. And the sum of all the things you distribute is equal to E, not to 1, to E. So you are distributing the full estate. And I introduce the simplest way to distribute this money is proportional. So this is very simple. It's proportional to what everybody claims. Then we have another one, which is constraint equal awards, and a third one, which is constraint equal losses. So I introduce these three. And right now, I'm going to introduce two more before moving to the last two sections. If you have any question, you can interrupt me. And if you need chocolate, please help yourself. It's on the table. Maybe only you can take the bag and make it turn around this room. Okay, so two additional division rule. Last week I didn't introduce them. One is, this is number 4 because we have already 3. One is called random arrival. So what is the idea? You are one of the people who claim the money. You go to the person who is in charge and you ask for your claim, DI. And you are going to get, so let me tell you the rule. When a player or an agent, when an agent arrives, he receives the minimum between 0 and his claim, and sorry, no, between his claim and his claim and what is left. So this is a rule. You go to the agency which is going to distribute this money, and you are going to receive the minimum between what you claim and what is left. However, this is unfair, because if you rush and are the first one, you would get probably your claim, while if you just take time and you are the last one, you will probably not receive anything. So we need to make this a random process. So we mean to average over all possible order. So the first, everybody can claim what he would like to claim, but the arrival is going to be random, and we have to take the expectation, so we average over all possibilities. So I'm going to, so for fairness, I write a sentence and then I give you the formula. For fairness, because otherwise it's related to speed, the random arrival rules, the random arrival rule is assumed or is imposed. So let's see what it means. So I need to look about permutations because we need to take into account all possible order. So I remind you one notation. Let capital pi, this capital pi of n be the set of all permutation of n elements. So what is a permutation? Remember, if I take 4 elements, a permutation is, let's say, 2, 4, 1, 3. So this is a permutation, and I call small p is a permutation. So it means small p is an element of this capital P of N. It's one permutation. So you take these 4 players and randomly you change them. This is a permutation. And I need to introduce one more notation. I'm going to write pi smaller than I. It is a set of J inside N so that pi of J is strictly small. So think about it. I do a permutation. For example, I take I is equal to 1. Pi of 1 in this case, it's going at the 3rd position. And then I look at those J which are before. So these are the these two, let me put in blue. These 2 numbers, 4 and 2, are the ones which are smaller than pi of I, if I is, I said is 1 in this case. So the set of J, so that pi of J is smaller, strictly smaller than pi of. Why? Because what is the idea? I'm going to do a random reorganization. And remember, the arrival order is important. So I'm looking at those arriving before. That's the idea. I look, so now the player 1 is taking the 3rd position, and I'm looking at the players which are arriving before. And so what is this division rule? What is the formula? So the division rule is F. I remind you, I use F for this section for a division rule of NED. So N is the number of players, E is the estate, D is the claim. So let me write a formula and we will understand. Of minimum. Oh, I need more space. So just here, I continue here. Minimum between DI and maximum between 0 . Okay, so let's check that it's meaningful. This 1 over n factorial is because altogether we have n factorial permutation. So I do an expectation, I do an average. This n factorial means simply I'm going to sum n factorial terms, so I need to divide by n factorial. And then I take one permutation. So I choose an arbitrary order, and the player I is going to receive the minimum between his claim and what is left. And what is left is we want something bigger than 0. And the total estate minus what has already been distributed to the person who arrived before. So this is in a formula exactly this idea. The guy arriving at position 3 is going to receive either his claim or what is left. But we randomize by taking all possible perturbation and divide by this factor. Yes?
Comparison pi j less than pi r, is that comparing two permutations?
Yes, look, this picture is explicit. I assume I is 1. 1 is going to be the 3rd one arriving after this permutation. It takes the 3rd position, and I look at the 2 players which are arriving before. player. So this is the players which, after permutation, are arriving before.
But pi is the entire permutation, right?
Pi is a process from 1, 2, 3, 4 to 2, 4, 1, 3. So pi of 1 is this number 3. Pi of 2 is 1. Pi of 3 is 4. And pi of 4 is 2. So indeed, 2 and 4 are arriving before this one. So yeah, I think it's, if you think about it, this rule, when we randomize the arrival, so we take all possible arrival, we get this formula. So this is called a random arrival. And there is a last one, a last distribution rule, which has different name. I put a link, I think. So this is number 5. It's called, I think the first name is for historical reason. I don't fully understand it. Contested Garment rule, but it's also equal to concede and divide. Names are not so important in this case. And it's also called the Talmud rule. What is the idea? I will explain. So if the estate, so if the remaining money is either smaller than, or strictly smaller than the sum of all claims divided by 2, or equal to the sum of all claims divided by 2, or bigger than the sum of all claims divided by 2. So we have 3 cases. If it is equal, it's easy. If what is available is equal to all claims divided by 2, then you give exactly di over 2 to everybody, I mean, to each person. Then if it is strictly smaller, you apply the second rule I have introduced or recall, and I will write a formula. Apply second rule to di over 2. And the third case is you give di over 2 and apply the third rule to the remaining, or to the, yeah, what remains. So, and I'm going to write one more formula for this. But so we have 3 cases. Either it's strictly smaller, or it's equal, or it's strictly bigger. If it's strictly smaller, you apply one rule, the second one I introduced. If it is equal, you just give di over 2 to each player. And if it is bigger, you first give this di over 2, and then the difference, you apply a certain rule. So what does it mean? So no, here there is no order at all. The amount is decided without any arrival. The arrival was in the previous rule. Wait, let me write the formula. So it's called FCG for contested garment of NED. And I give the definition. So, and so what you give at player I, so we have 3 cases, but one is easy. You give di over 2. I don't write the condition. So this is the first condition, this is the second one and third one. Then you give the minimum between di over 2 and lambda. And I have to write a condition on lambda, like we did last time. And you give di over 2 plus the maximum between 0 and di over 2 minus lambda. So if you look back at what we did last week, you should see in the second rule was this one. The third rule was this one. And with lambda satisfying that the sum over all I of n of f Cj of n e di is equal to. So we want to distribute the entire estate. So you should recognize this from last week and this one as well. So this is a fifth division rule, which is applied in some cases. Yes?
Be equal. Wouldn't half the estate be remaining once you allocate?
No.
The
If the estate is equal to half, so if everybody is claiming a certain amount, but I have only half, I give half to everybody, half of what this person claims. No. I told you at the beginning, this estate is less than the sum of all di. In this case, it's one special case. This estate is exactly half of all claims. And if it is less, we do a certain rule. If it is more, we do a certain rule. And apparently, it has some historical application, so that's why it's called Talmud rule. And now the final theorem in this section, which is a bit interesting. I will tell you why. The final theorem tells you that this FRA of n e d, so this is a random arrival, is nothing but the Shapley value of the corresponding game NV. I introduced a TU game for any bankruptcy problem. And the second statement is that this Cj of NED is nothing but the nucleus of NV. So what does it tell you? You should think about, first I was a bit disappointed by this, but in fact, no, you should be very happy with this. Why should you be happy and not disappointed? For the following reason, these guys have been defined abstractly for all TU games. We gave a formula. And you can wonder, oh, is this formula meaningful? And the answer is yes, it's meaningful because in some games, here's a bankruptcy games, we get something that we can understand. We can interpret, this is a random arrival. I gave you the explanation why we have this. This is a different rule, which has some history. So it means these abstract division rule, or it was introduced as allocation rule, when you apply them on a concrete example, you get something meaningful. So this is a good point. And not that, in a sense, it's too easy. No, it means that the abstract notion gives you very realistic or very concrete allocation rule or division rule in concrete examples. And what you get for free is plus 4 properties, because the Shapley value respected 4 conditions, and the nucleus also had some special properties. So for free, you get that these division rules satisfy some conditions. All right, any question or remark?
With the contested garment rule, is the like set of distribution, is there a set of distributions or is there one distribution that the rule outputs? Because the nucleolus, if I remember correctly, is a set of points.
So it means, but in some cases, it's just 1 point.
Okay.
Yes. So
But
it
the Chapler value is 1 point in the.
yes. But in this case, I don't know if it is a convex or game or not, but yeah, you're right. The nucleus was a set, but in some cases, it's just 1 point. The same for the core. The core itself is sometimes just 1 point, while the general definition is a set.
In that contested gun.
Okay, if you want, you can probably develop your own rule. It will be Heavideal's rule, and you can put a third. I mean, all these are, but yeah, if you don't put a half, you will not satisfy this. But I mean, for the allocate, you can also decide you take all the money and you give nothing to the other one. That's also a rule. I mean, we need to define a rule which respects some conditions that we think are fair or correct. And in particular, the Shapley rule satisfies 4 things. But you can also take all the money and say goodbye to everybody. Okay. Next section, I want to go quickly through this section because I want to spend more time on the next one. But still, this one is interesting, is the voting problem. So I will be sketchy, but I wrote more in the notes. What is I remind you, reminder. We know what is a simple game. A simple game is a game which takes only 2 values. V takes only 2 values, 0, 1. So it means V of S is always inside the 0, 1 set. And in addition, they are monotonic. So more player means you increase the payoff or the utility. And V of N is always 1. For the grand coalition, it's 1. And the set of simple game is denoted by Sn. And the voting problem is quite important because when you need to take a decision, something is going to apply if and only if, let's say, the value 1 is chosen, while you don't apply this thing if the value 1 is not reached. And for simple game, I still introduced what is called the winning coalitions. The winning coalitions are the subset of S, sorry, the subset of N, so that F of S is 1. These are the winning coalitions. So W is a set of all winning coalitions. And I also introduce the set of minimal coalitions because it is monotonic. So if you have a coalition which is a winning coalition, so it means V of S is 1. For all coalitions which are bigger, you get still 1 because it's monotonic. So there is a nice definition in this, which I think is worth introducing. So I consider a simple game. A simple game is a weighted simple game. So this new is a weight. What is new? It's a simple weighted game if there exists a number Q which is bigger than 0, and there exists P1 up to Pn which are positive numbers, such that V of S is 1 if and only if the sum of the Pj or Pi. So what does it mean? It means I associate a weight, a number, which can be any positive real number, to each player. And the coalition takes the value 1 if the sum of the contribution for each player is bigger than a certain Q. That's the meaning. So each player has a certain weight. You weight more or less than another one, or maybe it's the same weight for everybody, it depends. But it's called a weighted simple game if we get 1 whenever the sum of the contributions is bigger than a fixed Q. And let me give you an example, and I think it's quite explanatory. It explains the content. It's the United Nations Security Council. So probably you know that it has 15 members, but 5 are more important. 5 more important. Because when they vote about something, these 5 have to say yes, and it's necessary that 5 hours, 5 or 4, 4 others also say yes. And how we can represent this with this game? So we set Pi is equal to 7 for these more important countries, for these 5 countries. You set Pi is equal to 1 for the other 10 countries, and you fix Q is equal to 13. And something is accepted if and only if the rule, the sum of this contribution is bigger than 39. So you can check. You need all 5. It gives you 35, and you need 4 more. And if you don't have these 5s, you cannot get 39. So if all the other ones give you 1, you cannot reach 39 without these 5. So this is one way to encode this very specific rule of the Security Council into just one framework. So I like this example. Now, voting problems appears quite often. What is the question, Muyan?
Why did it add you?
Oh! Sorry. Sorry. I'm used to MU. Sorry. That's nice mistake. It's a permutation. Yeah. Okay. What is an allocation rule for? So I gave you one definition, but what is an allocation rule for simple game? So we look for allocation rule. For simple game. There is one problem. What is a problem is the additivity. Remember, I mentioned additivity many times because it has to be respected by some games or some allocation rules. Additivity is not meaningful. Why? Because the sum of 2 simple games is not a simple game. The image of V has to be either 0 and 1. If you do a sum, you can get 2, which is not correct. So you need to change this. And for this, we define something which I could have introduced a long time ago, but it's a good opportunity to do it. What is a maximum game and what is a minimum game? So start with two games, two given NV and NW TU games. The maximum game, these definitions are quite natural. The maximum game, which is denoted by NVW, it's a notation, is given, is defined by. So I need to tell you who is this V, this sine veg or inverse veg, W of S, so apply to S. It's, as you can expect, it's a maximum between V of S and W of S. And I can also define the minimum game. So we define also the minimum game, which is this time a veg. It's a different notation with this as a minimum. Okay. That's, you can do it for any game, any two games, TU game. And the good point with simple games, this is an exercise. If you start with two simple games, this is still a simple game exercise. If NB and NW are simple games, then max, so let's say no, N with VW and N with V veg W are simple games. So it means that with, I produce again a simple game, either with a maximum or with a minimum. So it means with this, I will be able to define an analog of addition, but instead of addition, it's going to play with maximum and minimum game. So what is a property I'm going to define, and then I set an allocation rule. It's called the property of allocation rule. I mentioned many for the last couple of weeks. I mentioned many, but this is a new one. It's called the transfer property. And it's going to replace the addition. So the allocation rule will phi four simple games. Four simple games satisfies this TF, it's called TF. TF conditions. If for any NV, NW simple games, we have phi of n with minimum game plus phi of n with a maximum game. These are two games, so I can apply phi is equal to phi of NV plus phi of NW. Okay, it's a definition. I would be happy, probably it's a bit late, but I would be happy if somebody tried to understand this on a concrete example. What means this condition? Additivity, it was meaningful. We could understand what is the addition of two games. Now, this is slightly different. It's you construct this. The first one is a maximum. You construct the minimum. You apply phi to both of them, and it should be equal to the sum of the phi of the original games. That's a definition, or that's a condition. So I would be happy if somebody look for an example, because we always learn by working on concrete examples. You know, the theory is not constructed from nowhere. People who start with examples, and then they try to generalize and construct the theory. And what is the main theorem in this section? The Shapley value. But it has also another name in this context. The Shapley value, it's also called Shapley-Shubik. Index, another name in this context, is a unique allocation rule, is a unique phi from Sn to Rn. So a way to distribute the value satisfying four conditions: the efficient condition, which is meaningful for simple game, this NPP condition, which was about null player, the symmetry condition, and the last one I have introduced, this FT or TF. So again, we have a characterization of one way to distribute this. Okay. There is just a remark, and then I go to the last section. A little bit more is written, but let me just make one remark. The Shapley value contains a certain expression. When you compute the Shapley value, contains V of S union I minus V of S. It contains many expressions like this. Okay. But look, here we are for simple games. So these two guys take only two possible values, either 0 or 1. If both are 0, that's not very interesting. If both are 1, they cancel. So the only interesting case, so this expression, this is interesting, or it gives a contribution if V of S union I is 1 and V of S is 0, which is equivalent to S union Y. S union Y is a winning coalition, and S itself is not a winning coalition. So it means you can concentrate on, given I, you can look for all coalitions such that this property holds. And this is called, it's written in the note with more detail, it's called S is a swing for I, because S without I is not winning, but S plus I is winning. So it's a swing coalition. I refer to the notes if you want to know a little bit more. The theory for this section is quite developed because the voting problem is an important one. but there is a huge literature really on this. So, but I promised to do a last section about evolution, so I need to switch to the last section. Okay, so the last section is about evolution or evolutionary game. So this is 6.5. Evolutionary game theory. Now it's a well-developed theory. People want to understand or describe the evolution with game theory. So they want to use the tools from game theory to understand the competition between species or understand or model the evolution. So main idea. You cannot really explain, but at least you can describe, model the evolution of species or individuals using tools from game theory. And we will just see that it, at least the first approximation, it works. And of course, then the literature is very large. And I gave you 2 references that we have in the library. But we need one more ingredient. Compared to what I have introduced so far, we need the notion of time. This new ingredient is a time. So far, time didn't play any role. While evolution, of course, it's a time-dependent problem. So I need to introduce time. Let me remind you what we did in section 2.5. So the framework for starting framework of section 2.5, which is the section about finite strategic game. I will recall what we need: strategic games with matrices. So when I started strategic game in chapter 2, first I did not introduce matrices, but if we have a finite number of strategies, we can use linear algebra and matrices. So what was the framework? L, I just recall what is already in section 2.5. This set L from 1 to L is strategies of player 1 for 2 players. And M is going to be the set 1 up to M. It's a list of all strategies of player 2. I'm assuming that the first player has L strategies, the second player has M strategies. And we introduce matrices. So we introduce a matrix A or B of size L times M of R. And we also introduce X, which is a vector in SL. Remember, it's a set of X belonging to R plus our L. So it's L entries positive, such that the sum of xi, I from 1 up to L, is 1. We introduce this. And we introduce also y in Sm. You just replace the y in R plus M, so that the sum of yi, now you sum from 1 up to M, is equal to 1. What they represent, these are mixed strategies, because we have L pure strategies, and we can take linear combination of pure strategies, and the same for the second player. And what was the payoff? Let me just remind you, the payoff was computed at that time. The payoff for the first player, if he used mixed strategy X, and the second player used strategy Y, was given by this formula. And the payoff for the second player, if the first one used X and the second one used Y, was given by this formula. XT is a transpose. So you can check it's a product. So it's a matrix applied to a vector, and you do scalar product with X. Okay, so this is a reminder of section 2.5 with the notation of section 2.5. I've written a little bit more in the notes, but that's in all what we need. And let me just remind you one more thing. I consider what is I from 1 up to L is a basis of R L. And what is EJ is simply the vector 0, 0, 1, 0, 0. And this J is at position J. And observe that this EJ is an element of SL. In fact, it's a pure strategy because it uses only one strategy. So this is a pure strategy. It's not a mixed strategy, it's a pure one. And so we have L pure strategies for player 1 and M pure strategies for player 2. Any question? So I know it's already probably 3 months old, but yeah, this is what we have, the framework of section 2.5. Now, so what do we want to do? Now we want to have, up to here we had 2 players. Now I want to have a large number of players. And I will assume 2 things among these players. In fact, I have an infinite number of players for this presentation. So we consider a population. Of course, this is the first model. You can then extend to more complicated, but the first model is we consider a population of indistinguishable individuals. So you cannot distinguish them except in the way they interact. So what does it mean? Each of them use a pure. For now, I assume that each of them use a pure strategy. A bit later, they will be allowed to use strategy. Yes, a little bit later, they will be allowed to use mixed strategies. But for now, I'm going to consider a large number of individuals that cannot be distinguished, but each of them use a certain pure strategy. And so it has some consequences. The fact that these are indistinguishable means I don't have 2 players, but I'm going to consider, so this fact implies that in fact B is going to be A transpose. Because we cannot distinguish player 1 and player 2, it's natural to have only one matrix. It's not always a zero-sum game, but we consider B is equal to A transpose. This is called a symmetric game. The definition of a symmetric game is when the transpose of B is, or B is A transpose, or it's the same, but in the note I've written, transpose of B is A. The same. But it implies something. It implies that the game is fully determined by A, and it has to be a square matrix. The N is chosen for simplicity. I could use L. But because most of the theory has been constructed with N, I decide to use N for here. Because of this condition, this matrix has to be a square matrix. So we are dealing with symmetric game. And now we assume that a fraction xi is between 0 and 1, of the population. Use strategy. The pure strategy. The pure strategy. EI, I remind you that I denote by EI a pure strategy, and this is an element of, okay, no, just keep EI. So we have a full population, and I'm going to say this part use the strategy 1, this part use the strategy 2, this fraction use the strategy 3, and this one use the strategy 4. Xi represents the fraction of the full population, so it means that the sum of xi has to be 1. But this is equivalent to x belong to Sn. It's just the definition of Sn. So we have a full population, and a fraction is using, I told you, for now, each group use only one pure strategy. Right? So if they use one strategy, they have an average payoff. So a player with strategy EI has a payoff, an average payoff. So I will explain this idea. An average payoff of EI transpose AX. Why? Because what is the idea? This player randomly is going to play with the other members. But the other members are distributed with these fractions. So it means on average, he will play with, again, a player of type 1 with this probability of this fraction x1. He will play with an element of this second part with a probability x2 and so on. So on average, it's going to have a payoff of this or utility of this, and this is nothing but AX N3I. Just think about linear algebra. when you do the scalar product with the vector 0, 0, 1, 0, 0, you get this. And so this is a player with strategy EI has an average payoff of this. This is the first observation. And the second observation is the average payoff among the population what it is. It's the sum of xi time what we have just obtained, AXI. Why? Because this is for one individual, but the percentage of this individual is x1. Then if we do the average, we have the same expression for the second type, third type, and fourth type. And we observe that this is nothing but XAX transpose. So it means the average payoff among this population is nothing but this expression. Okay? Any question? So it's, in fact, it's just a way of thinking about mixed strategies in a different way, but it's nothing very different from this. Okay, so now I need to add the time dependence, because look at this picture. Suppose at the beginning we have this distribution of the population, then this can depend on t, which means that if I put a t dependence, let's say when t becomes bigger, maybe the proportion of x1 will become bigger, the proportion of x4 will become smaller, and so on. So this fraction will change over time according to a certain rule. So now we put the time dependence. Assume xi, this fraction is in fact depending on t. It can change according to the time. T is the time. But now I need a dynamic. I need to say how it's changed, and this is a key point. So I'm going to consider the derivative. There is a standard notation with x dot I of t. This is d over dt of xi of t. So I compute the derivative. Of course, it means this function is differentiable, but it also means in order to justify this differentiability, I need a set of individual to be infinite or to have densities. I cannot have just 25% because if I have 25%, it won't be differentiable. So it's an assumption. The derivative exists. Okay. And I want to consider, so if we have this notion of derivative, one thing is very natural, is this ratio. Then, so this represents the velocity of change, the velocity of change of the fraction of change of xi. How fast, if the derivative is big, it means xi is changing fast. If the derivative is small, it means xi is more or less constant. So we consider a natural thing is this quantity. I don't write the dependence, but now these are function of t. And I assume that the denominator is not 0, of course. This is a growth rate of the fraction or growth rate of xi. And now I need an equation for this. How this growth rate evolve. So you can guess. This is a payoff for player I. This is the average payoff. If you get a better payoff than the average, you are going to increase. I mean, people want to get more. So if your strategy is a winning strategy, probably the fraction will increase. While if your strategy is worse than the average strategy, probably the number of people who want to use this strategy is going to decline. So this is natural to put this equal, so this quantity equal to AXI minus XTX. Because this is the difference between what player I get on average compared to the average among all the population. And now if I rewrite this expression or this equation, we get this equation. And this equation is rather famous. It's called the replicator equation. Thanks to Nguyen, we had already a report on this a long time ago. But now I think we just, it's a model, of course, but we justify how, oh, there is a xi, there is xi missing here. The derivative of xi is proportional to xi times this difference, which means this difference is positive if on average your strategy is better than the average strategy. So it has a meaning. And now once you have an equation, you can study it. And this is the subject of next semester. Next semester, we are going to deal with differential. This is a differential equation. And it's also a dynamical system because now we can study the solution, the function t goes to x of t. By the way, it's an element of Sn, remember, satisfying this equation. Its derivative satisfies this. So it's a differential equation. Just, I want to make clear about one thing. I'm sure you wouldn't do this mistake, but just let me. Xt has to be always, to sum up to 1, because these fractions have to end up to 1. But it doesn't mean that x dot belongs to Sn. The derivative has no reason to be normalized. So just be careful about this. This is clear, but there is no reason why it should be inside. So let me give you 1 or 2 examples. Or do you have any question? I'm not claiming that this, it looks rather simple. For n is equal to 2, so what is n now? In this framework, n is 2 things. And we will change this in a second. It's 2 things. It's a number of pure strategies, but it's also the number of different types of individuals because each of them has a pure strategy. So we have n pure strategies, so we have n types of individuals for now. So let me give you an example. When n is 2, which is not completely trivial, n is equal to 2. And I'm claiming that the most general matrix has this form, 0b a0. Why I can put 0 on the diagonal? This is an exercise. You can start with a matrix A, B, C, D. This would be the most general 2x2 matrix. But if you think about this equation, you can subtract A in the first column, and it doesn't change this equation. And you can subtract D in the second column, it doesn't change the equation. And if you do this, you obtain maybe not exactly the same value, but you obtain a matrix which is 0, something, something, 0. No. It was a relation. No. A has not to be of any type. The relation was B transpose is equal to A, because we reduce a problem with two different matrices to a problem with only one matrix. But A can be quite general. So I'm claiming that this matrix is in fact enough to understand what happens. You don't need the 2x2 arbitrary matrix. You can subtract things so that you have 0 on the diagonal. But it's a result of an exercise. So if we take this and now we consider x2, of course, x2 has to be 1 minus x1 because the sum of x1 and x2 is 1. So it means I can just write x for x1, and then 1 minus x is x2. I just simplify the notation. And this equation here, so if I use a matrix A of this type, and if I use this relation between x1 and x2, the replicator equation in this special case is x dot is equal to x 1 minus x times A minus A plus B x. So this is the most general equation of this type for n is equal to 2. And you can study it. And what does it represent? So A and B are two parameters. Depending on what you want to represent, they have a certain physical meaning or biological meaning, of course. But now you can study this equation. Remember that x has to be between 0 and 1. So you have boundary conditions. X cannot become larger than 1. It cannot be smaller than 0. X is between 0 and 1. But you can study this equation and you will observe different things depending on A and B. So what you observe, for example, so observations. X is equal to 0 is a stable point, or x is equal to 1 are stable points. Because if you choose x is equal to 0, it makes 0 on the right-hand side. The derivative is 0. Everything is stable. It means you have a population of only one type, and they have no chance to become something else. Or the same for the other one. But there is another one. It's written in the notes, depending on A and B, if this can vanish, you have one more stable point. So it depends on if this has a solution between 0 and 1. Depending on AB, it can have a third stable point. And even if you are not at a stable point, you can study the evolution, how this evolves according to time. So what does it represent? It represents two populations which are competing with these two parameters. And the ratio between these two populations can change over time. Now, an example of n is equal to 3. There is one famous example, especially in Japan, For n is equal to 3, an example is a famous example. This famous example is rock, scissors, and paper. So what is the corresponding matrix A? You can think about it. It's 0 on the diagonal, because if the two players propose the same thing, you get 0. You have 1, minus 1, minus 1, 1, 1, minus 1. You can think about it. And by the way, it's a zero-sum game. So you have to come back to the meaning, but you can check it's a zero-sum game, which implies that on average, this XAX transpose is 0, and you know it. If you are two players and you play this on an infinite number of times, nobody is going to win. Half of the time you are the winner, half of the time the other player is the winner, as long as you do it randomly. But it has a consequence. We have four stable points. Of course, everybody always plays the same thing. Nothing happens. Or if all players play 1/3 each solution, it's a stable point. Okay, so we have 4 stable solutions for this. 4 stable for this. In R3, be careful now, we are in I should say in S3, because these fractions have to sum up to 1. So the solution are 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1/3, 1/3, 1/3. Now you can study, it's still possible to study the general solution. The general solution for any A in M3 of R, but it's already very long because you need to list all possible cases. So you can always have 0 on the diagonal by the trick I mentioned, but still you have 6 parameters. If you consider the most general matrix with 0 on the diagonal, you have 6 parameters. So it's already a long work. And for n is equal to 4, I've seen that there is no systematic solution. So already for n is equal to 4, many things can happen. And in particular, you can have some cycle. So you should think I can only do a picture in dimension 3, but you can have a cycle, which means your populations are going to change on a periodic in time. Or you can have one periodic system which is attracting. So it means if you start with a condition slightly different, then you are converging to this. Or you can have chaotic attractors. I will mention this next semester. So already for n is equal to 4. So it means you don't need a lot of degrees of freedom in order to have very complicated things. Okay, we still have a few minutes. I want to mention 3 extensions. Of course, people have developed this a lot more, but let me define 3 directions where we can extend everything. The first one, I told you I don't want to have only pure strategies. So I can extend it. Each individual is allowed to have a mixed strategy, which is quite natural. So the first extension each individual can have a mixed strategy. So it means I need now two different numbers or two different things. So I need the type of the individual, type of individual. The type is going to be I between 1 and n. So I'm going to keep n types of player, and each one, so it means a fraction of the population is given by x belonging to Sn, because we have n different types. So the different fractions have to sum up to 1. So this is exactly the definition of Fn. But now each of them can have a mixed strategy. So for I between 1 and n, Pi is an element of SL, which is a mixed strategy made of L pure strategies. So it means I have a game with L pure strategies, and for each I, they can choose a mixture of these L strategies. So it means each player choose a mixture of L strategies. Okay. So we set, I need one more thing. I set P of x is a sum I from 1 up to n, xi P of I. So be careful, what is this object? This is just a number. This is a vector, so I sum vectors with some coefficient. So it means this is an element of SL. No, sorry, of S, not of RL. RL. And these are positive. And now what is the replicator equation in this case? It's the same idea. If you perform better than the average, then your ratio or your fraction is going to increase. So this replicator equation, in this case, it's going to be for I from 1 up to n. So for each type of players, we have x, the derivative of xi is xi times pi minus p of x transpose a p of x. So it's just a bit more complicated, but it's the same idea. This term is the average on the population, but each one is using a mixed strategy. So we are dealing with the sum of all mixed strategies. And this is what you get as individual I. So if this Pi transpose APX is bigger than PX transpose APX, then your ratio will increase, otherwise it will decay. So this is in order not to have the restriction about pure strategy. So this in one extension. The second extension, which I just mentioned, is a payoff need not be linear. Indeed, this theory is linear in the sense that we are dealing with a matrix applied to a vector. This is a linear thing. But there are plenty of games where you have nonlinear effect. For example, if you need interaction with 3 players at least to get something, it's very quickly nonlinear. So we change A applied to X to something more general, a function of X, which is not linear. But of course, nonlinear problems are much more difficult in general because you cannot use linear algebra. So A of X, nonlinear. So by the way, what you do usually when you study a nonlinear problem, you decide, oh, I want to study near a certain value, and you do some Taylor expansion near this value, and then you linearize. So I will mention this next semester. So a nonlinear problem, locally, you linearize it because this is something you can do. And then you study close to this point what happens. Do you escape from this point? Are you attracted by this point, and so on? So linear approximation is going to play a big role. And the last extension, it's non-symmetric. You remember at the beginning of this discussion, I said B transpose is A in the sense that all individuals are indistinguishable, but quite often you have 2 species which compete and they don't get the same thing. So you have no reason to always assume it. It means the payoff for one species can be related to A, but you can describe the payoff for the other one with B because it's different. But then you need to not only play with one matrix as I did, so you need to deal with 2. So you need to, there is probably one version of the replicator equation where you have two types of evolution, one for one species related to A and another one for another species. But yeah, people have worked a lot, so you need to open some books and look for this. Okay, that's all what I wanted to say. Thank you. I know it was not easy, but I think it was also an interesting course. Probably for physicists, it was less applicable compared to other subjects. Still, it's closer to what we can feel because this voting problem or bankruptcy problem, I hope we don't face it every day, but this is something that, yeah, we can meet on a regular basis. And finding a rule to distribute some utility or distribute some money, respecting some properties, is something that we have to deal with on a regular basis. So it's also interesting. Thank you, and hope to see you next semester.